You are still live. Can you take the microphone?
Ah.
You could have carried on talking. Sorry.
Thank you.
Second speaker for this morning is Amal Omrani, and she will be speaking on concentration inequalities in Riesz spaces.
Thank you. Hello, everyone. I am very happy to meet you in COSA conference, and I'm grateful for Amin for making it possible. So today I will give a talk about concentration inequalities in Riesz spaces, which is a joint work with Mohammed Amin bin Amr. So first of all, I will introduce the main reason that led me to work in the study of concentration inequalities. Then I will give some preliminaries about the probability theory in Riesz spaces. As a third step, I will define the moment generating function in the framework of Riesz spaces. To do this, I will define the exponential function in the framework of Riesz spaces and derive some of its property. Then I will give the moment generating function definition. To finish, I will give some of the concentration inequality in Riesz spaces, which are Chernov's inequality, which is now published in the QM journal, and then Binet's inequality, Hoeffding bound, and to finish with McDermid inequality. So this work is the first step of a very ambitious project, which is to study machine learning in Riesz spaces. Actually, in the classical case, in the probability theory, to study the stability of machine learning algorithms, the main tool used is the concentration inequalities, and mainly Hoeffding bound and McDermid inequality. And happily, the ground is prepared thanks to the work of Labuschagne, Q, and Watson. We have several tools to use, such as the conditional expectation, the notion of the notion of the conditional independency, the Markov processes, the martingale, the Bernoulli processes are well defined and widely used in the framework of Riesz spaces. So I will start with defining the probability space and then give the analog in the case of Riesz spaces. In probability theory, a probability space is a triple omega f p, where omega is the sample space, f is a sigma algebra, and p is a probability measure. And in probability theory, we work with random variables, which are measurable function from our sample space to a measurable space. So in the Riesz case, we work with the triple that we denote the conditional Riesz triple, which is E, capital E, little e, and T, where E is a Dedekind complete Riesz space, little e is a weak order unit, and T is a conditional expectation. So let me define what is a Dedekind complete Riesz space, what is a weak order unit, and what is a conditional expectation. So we all know that Riesz space is a real vector space, which is a lattice, and it is a Dedekind complete whenever a non-empty subset which is bounded above have a subpromum. Now, to define the weak order unit, I need to recall the definitions of an ideal, a bound, etc. So an ideal is a Riesz subspace which is solid. A bound is an ideal which is order closed. And the smallest
Slide.
There are a lot of stuff because when it's just back, what is stopped? Audio, sharing slides, sharing recording.
It doesn't.
Who doesn't change
Well,
sign?
can't do it. The other way. Okay. Okay.
Okay, change.
Yes.
Ah,
Oh,
So here, when we have the projection property, we can talk about the band projection, which maps every element with each part on the band. In our case, we work with Dedekind complete Riesz spaces, so we don't have to worry, because if it is Dedekind complete, then we have the projection property, and so we have the principal projection property. Now, let me recall the definition of conditional expectation. So in the Riesz, in a Dedekind complete Riesz space with a weak order unit, a conditional expectation is an operator T from E to E, which is a positive projection order continuous, mapping weak order unit to weak order unit and having a Dedekind complete range. So let me give the analogy between the classical case and the Riesz case. So the probability space is the triple omega f p. The analogous will be the conditional Riesz triple e T defined previously, and we will represent the function one by the weak order unit, the events by the order projection, and the indicator functions by the band projection. So, for example, if we would like to give analogous of the probability of a random variable greater than epsilon, we can take the conditional expectation of the band projection on the positive part of f minus epsilon e, where f is an element of our Riesz space. This must be here and this must be here. Okay. Also, the concept of independency relative to a conditional expectation has been generalized to the framework of Riesz spaces. Actually, we can define the T-conditional independency of two band projection. In fact, if we take P and Q are two band projections, then they are said to be T-conditionally independent if we have TP TQ of E is equal to TP Q of E equal to TQ TP of E. Thanks to this definition, we can define the T-conditional independency of two Riesz subspaces E1, E2. Actually, they are said to be T-conditional independent if whenever we take two band projections P1 and P2, such that P1 is a component of E1 and P2 is a component of E2, then we have those two band projections are T independent. Also, we can define the T-conditional independency of a sequence of element of E. Actually, if we take the closed Riesz subspaces generated by Fn and Rt, then the sequence Fn is T-conditionally independent if we have those Riesz subspaces are T-conditional independent. Okay. So the objective of this section now is to construct an equivalent definition of the moment generating function. To do that, we need to define the exponential function on the Riesz spaces. So from now, I will assume that E is Dedekind complete Riesz space with a weak order unit U, and I will work on the ideal generated by U. I will denote by x to the power of 0 the unit element U. If we take the power series of x to the power of k divided by factorial k, then this series is order convergent, and I will denote its limit by the exponential of the element x. So here we can prove easily that the properties that we have for the scalar exponential function are also valid here. In fact, we have the exponential if the sum is equal to the product of exponential, and for every element x, we have the exponential of the element is positive and it is invertible. Now we can define the moment generating function in Riesz spaces. If we take an element x in EU, then mx will define the map from R to EU that takes t and give the conditional expectation of exponential Tx. x. Mx will be called the moment generating function of x. So here we can prove that if T is a strictly positive conditional expectation on a Dedekind complete Riesz space with a Hugh-order unit, then if I take F and G are two T conditional independent elements, then we have TFN GM is equal to TFN TGM equal to TGM TFN. Indeed, as F and G are T conditionally independent, if we consider EF the closed Riesz subspace generated by the range of T and F, and EG the closed Riesz subspace generated by RT and G, then those two closed Riesz subspaces are T independent. So thanks to the Radon-Nikodym theorem, there exists two conditional expectation TF and TG with range respectively EF and EG, such that our conditional expectation T is equal to TF TG equal to TG TF. So if we consider TFN, then we can prove it is equal to TG FN. Actually, TFN is equal to TG TF of Fn. And here, as F belongs to the range of TF, then this quantity is equal to TG Fn. So as F and J play symmetrical roles, we can also prove that TGM is equal to TF GM. So let's go back to TFN GM. Here we can replace T by TG TF of FN GM. And here we have that F belongs to the range of TF. So it is equal to TG FN TF of GM. Now we have TF of GM. Now we can replace TF of GM by TGM, and it belongs to the range of T, which is included in the range of TG. So this one is equal to TGM TG of Fn. And now we can replace TGM with TF of, and now we can replace TGFN with TFM. Okay, thanks to this lemma, we can prove easily that the moment generating function of the sum is equal to the product of the moment generating function. Actually, here we can replace the moment generating function by its definition. And then we use the property of the exponential function. And here we replace the exponential by its definition. As it is order convergent, we can write it this way. And at this level, we can use our lemma to prove the desired result. Okay, now let me move to the first concentration inequality, which is Chernoff inequality. Actually, in probability theory, the Chernoff bound 1952 gives exponentially decreasing bounds on tail distribution of the sums of independent variables. So in the classical case, I would like you to notice here that the right-handed bound depends on the expectation, okay? So we managed to generalize this bound to the Riesz case. Actually, in the Riesz case, if we, let me mention here that we use Bernoulli random variables. Okay, so in the Riesz case, if we take EU a Dedekind complete Riesz space with a strong unit and T a strictly positive conditional expectation on EU, and if we take PG a Bernoulli processes with TPG of U equal to F. Let me recall briefly the definition of a Bernoulli process in the Riesz spaces. Actually, in the Riesz space, we have the definition of Bernoulli process. If we take E a Dedekind complete Riesz space with a weak order unit U and T a conditional expectation, then the Bernoulli process is defined as a sequence of T conditionally independent band projections such that for some fixed F in E, we have the TPK of E equal to F. There is a missing E here. Okay, so let's move back to our inequality. In the Riesz case, we managed to prove that the conditional expectation of the bound projection on the positive part of the sum dividing from TU is bounded by this quantity. It's nice here to mention that we managed also to give a conditional version of the Chernoff bound, which didn't exist in the classical case. Actually, if we take the particular case where E is equal to L1 and mu is the probability measure, and if we take sub sigma algebra G and we consider the conditional expectation given this sub sigma algebra, then we can prove that the conditional expectation of the indicator function of the sum given G is less or equal than this quantity. And we can take the particular case where the sub sigma algebra is the trivial one, then the conditional expectation is the expectation, and so we recover the classical Chernoff bound. In the same way, we managed to generalize the Binet's inequality. So in the classical case, Binet inequality 1962 provides a bound on the probability that the sum of independent variables deviating from a certain amount is less or equal than the exponential of this quantity. Here, let me mention that the right-hand side of this equality depends of the variance. So for Chernoff, it depends of the expectation. Here, it depends of the variance. So the same, we managed to generalize this bound to the Riesz framework, and we have this inequality. Okay, let us now move to the Hoeffding bound, which is the most important bound in statistics and machine learning, because it provides, it's a tool that can provide us a bounding of the probability of the mean sum of
No, wait 5 minutes. No, just here. No, don't move. There are no sound. Just you have you. I'm not hearing you on the internet.
Can hear me. Good. Okay. So the Hoeffding bound gives us a bound of the probability of the mean sum of random variables deviating from its expectation by a certain amount. And the beautiful thing about this bound that the right hand side of the inequality does not depend of the random variables, nor the expectation, nor the variance. So it's free from its random variables and it's free from its expectation. Okay, so also we managed to generalize the Hoeffding bound to the framework of Riesz cases. It doesn't work. I'm very lucky. Okay, so in the Riesz case, if we take x1, xn, g independent elements of our Riesz space EU, such that everyone is a sub-Gaussian. Here I managed to define what is a sub-Gaussian variable in the Riesz case. Then we have the conditional expectation of the bound projection on the positive part of the sum of xi minus their expectation is less or equal than this quantity. I would like to mention that the Hofding bound is used to prove the McDermid inequality, which will be the last inequality of this representation. So the McDermid inequality 1989 is a tool in probability theory that provides a bound on the deviation of sum of independent random variables from its expectation. And it is a very important result in the field of concentration of measure, and it is widely used in the analysis of random algorithm and in studying the stability of the machine learning algorithm. Okay, so in the Riesz case, if we take T, a strictly positive conditional expectation such that T is equal to E, and if we take Z1, Zn, anti-independent elements of E, if we take now a mapping from E to the power of n to E, such that the the image of Z1, Zn belongs to the closed Riesz subspace generated by RT and those elements. And if we suppose that the supremum of the conditional expectation of the image of those elements minus the conditional expectation of the same image, but here we change one of the actually here I need to mention that T minus 1 is the conditional expectation having a range generated by Z1, E minus 1, ZE minus 2, and we don't consider the ZE term. We replace it by another one. So here this quantity need to be bounded. In this case, we can prove that the conditional expectation of the bound projection on the positive part of this difference is less or equal than the exponential of this quantity. And here also we can notice that it doesn't depend of its expectation. Okay, we are still working now on Stein inequality, which will be the final preparatory step in our approach. And so we will be able to prove the stability maybe of the learning algorithm. Those are some of the references you may use. And thank you for your attention.
1 minute for questions.
Thank you. Okay.
Thank you for your very good talk. You showed us a connection between probability structure and Riesz space structure. My question is whether the way you model your Riesz spaces with some objects related to the ones of the probability structure are inspired by the probabilistic structure or not. I mean that finally, can you apply your theoretical results to other structures and the probabilistic structure? Do you have? Yes, yes. And do you have? Sorry. Do you have non-trivial examples when it's possible to apply this to another structure than the probabilistic one?
For now, I'm still in the theoretical part, but I'm always thinking of an example which might be not the case in the probability, but which where would this those inequality will be something we can use and we can choose in the probability case. Okay. I'm still thinking of some examples.
My concern is maybe it's just a projection between two structures that are the same. I don't know.
But in the probability case, we use the measure, the probability. Here, we don't use the measure, we only use the conditional expectation.
Yes, I know, but maybe is it possible to change your structure to a new one, to the positive one? No.
Yeah.
To partially answer your question, that there are results even here from this when you take it back to the probability setting that are new. which are the conditional versions of various of these things, which are not in the probability literature. So even taking it back to probability before you even take it to other things like machine learning and all that, you do get some new results. Well, the conditional versions of various of these things don't even exist in the literature. That's part of the motivation. Yes, we can. Actually, in some of our papers, okay.
Yeah, in fact, you will have like a integral or something like this, or probability space. In the case of Banach space, the space must be EL space, no? So the integral is an order continuous factional, so of the dual. So if you didn't have a strictly positive element in the continuous dual, you cannot have an integral. So if you cannot have an integral, you cannot have the classical case. Okay. So, but we build a conditional expectation type operator on spaces that we cannot have an integral. But the dual is trivial. So there is only 0 element in the continuous dual. Okay, so this theory is larger than the classical one. So we cannot transpose it directly. Okay.
Let us thank our speaker again. Thank you.